Welcome to this instructional video to finish up the start notes for Chapter 5. Wow! Protein-ligand interactions. Fundamental to all biological processes. Proteins bind ligands to do their jobs. And so let's think about broadly protein-ligand interactions. So let's say this is our protein right here. And if we zoom in on this area right here, that is where a ligand is bound. And so this molecule here is the ligand. And we would call this the ligand binding pocket. Or let's just call it site. Sometimes it's a pocket, sometimes it's a surface. We talked about that before. Ligand binding site. And so if the protein is an enzyme, we'll call this the active site, but that's Chapter 6. So this is where the ligand binds. There's a lot of good questions that need to be addressed in terms of protein-ligand interactions. And one of them is, how tight of a complex is it? How willing is the ligand to bind the protein in the ligand binding site? What is the affinity between ligands and proteins? And a lot of it's going to come down to an equilibrium such as this. Protein plus ligand is in association with the protein plus ligand yields a protein-ligand complex. So there's an association between protein and ligand. So this is what we call the protein-ligand complex. They are associated, typically non-covalently, although it doesn't have to be, but right now let's think about them forming non-covalent interactions. Also think about this being a dynamic situation. The ligand binds the protein to form the protein-ligand complex, and then it breaks apart. So the affinity between protein and ligand is going to govern how much of the ligand is actually bound to the protein at equilibrium. That's going to determine the affinity between a protein and a ligand. Well, table 5.1 here, it's actually a little small, and you don't really need to know any of these values, but we can get quantitative about this. We can get quantitative. I'm going to, on the next page, define something called K sub D. And this is a capital K. Let me make very, very clear that. K sub D. Sometimes that's a capital D instead of a lowercase d. That's okay. That's what we're going to call in a minute on the next page the binding constant or dissociation constant. Two names for the same constant. This is going to mathematically describe the affinity between the protein and a ligand. So again, kind of competing names here. We might call it the binding constant or the dissociation constant. So this is KD. Again, there's nothing to memorize about these numbers. What we're going to talk about is, on the next page, how to mathematically kind of determine the binding constant, and then what it really means in terms of protein-ligand interactions. I kind of like this graphic here. This just shows us that there's usually a range of protein-ligand interaction affinities, or binding constants, between proteins and ligands. And so, you know, the strongest, now notice the wording I'm using, the strongest, the tightest association between protein and ligands turns out to be something called biotin-avidin. Well, avidin is an egg white protein, and its ligand biotin, it has a very, very tight association, high affinity complex, and it is one of the strongest complexes that we know. On the other hand, when we get to Chapter 6, we'll talk about enzyme-substrate interactions. Those have to be weak. They have to be, we're going to say, hold on loosely. The substrate needs to bind the enzyme, or the ligand needs to bind the protein loosely, but don't let go, because the substrate's going to have to go toward the the transition state. So this is a kind of a theme in this class. There's no set binding constant for all protein-ligand interactions. They typically are all different, and guess what? Finely tuned to the function of the protein. All right, so let's get a little more specific about this. So let's say we have a protein-ligand complex. We can define two different types of constants, dissociation constant and association constant. Let me show you both just in case this comes up. So let's just do this right here. So protein plus ligand is in equilibrium with a protein-ligand complex. We can define something called an association constant. An association constant is an equilibrium constant. You know about these from general chemistry. Equilibrium constants are products over reactants. So here is mathematically the formula for an association constant. There we go. It's the concentration of the protein-ligand complex divided by the concentration of the product times the concentration of the ligand. The units on this, very important, is typically here some type of inverse concentration. So an association constant would be quoted with inverse molar or per molar, or for example per millimolar. Now let's talk about affinity. So look at this equilibrium constant here for that's called Ka, association constant. If you increase the Ka, what happens to affinity? Well, if you increase Ka, then that's telling you, if you increase Ka, that's telling you at equilibrium the protein, the ligand is going to spend a lot of time bound to the protein because you have a high value of Ka, and the protein ligand concentration is on top here. So as you increase Ka, or as you increase affinity, I guess, Ka will increase. And so higher Ka, higher affinity of ligand for the protein, and so this will be tighter binding. Again, tighter binding just means at equilibrium the ligand is more likely to be in the complex with the protein than not in the complex with the protein. That's really what affinity really means in terms of this. Now, that's association constant. Sometimes you'll see this, but most of the time we're going to talk about dissociation constant. If we do that, we need to define the equilibrium in a slightly different way. Let's say, oh, we have a protein-ligand complex, and it can break apart to the protein plus free ligand. So the protein-ligand complex is in equilibrium with protein plus ligand. When we do this, we can define K sub D. We just talked about that. The dissociation constant. It's also called the binding constant. It equals the following. Well, it's just kind of the inverse of what we had a while ago. All right. So the dissociation constant is this. And by the way, I think you just picked up on this. Ka is just 1 over Kd. And to be honest with you, most of the time we're going to talk about Kd values, not Ka values. But they are inversely related. So what about units for the binding constant or dissociation constant? It is concentration. And for example, it might be molar, millimolar, wow, nanomolar. All right. And so let's get back to this relationship between binding constant and affinity. The lower the Kd, in this case, we have higher affinity, which means tighter binding. So the lower the binding constant, the greater the affinity between the ligand and the protein, or we would call tighter binding. All right, so this leads us to the next page, which is how might one determine the binding constant or dissociation constant. If you make a plot, oh, here we go, we're making a plot. Everybody hang on. So let's just go from 0 here to 100%. So we're going to plot percent L in the protein ligand complex. What percentage of ligand molecules are actually in the protein ligand complex? Okay? And we're going to plot that against ligand concentration. And so let's just say it's millimolar for our sake here. Okay? Again, we're working off this equilibrium where protein and ligand associate to form a protein ligand complex. So what's going to be the shape of this curve? Well, I think you can imagine as the ligand concentration gets higher, the percentage of ligand in the protein ligand complex should increase. But if all the binding sites on the protein are occupied, then you're going to have a saturation effect. So we really have something like this. It's going to be like this, where it's going to level off. Now we can go at 50% right there, 50% of the ligands bound in the protein ligand complex, extrapolate over, hit the curve, and come down, and that is our dissociation constant. It's the concentration of ligand that it takes to get 50% binding in the protein ligand complex. That is the kind of formal definition of the binding constant. Now, something else we know, and you may come across this in the textbook or on other sources, this percent ligand in protein ligand complex, you can also plot here fractional binding. And we did this with, theta with hemoglobin and myoglobin. We had Y or theta, right? It was fractional binding. And so this really is what percent L in protein ligand complex is. In this case, we can get more defined. The theta here is the ligand concentration divided by K sub D plus the ligand concentration. So a plot of theta versus ligand concentration should yield a hyperbolic curve that we have here that levels off at higher ligand concentration. So you can think about it either way. You can plot percent ligand in protein ligand complex. Mathematically, that's the same as fractional binding, which can be defined as this. And so if you plot, for example, theta versus ligand concentration, you get a hyperbolic curve. Go to 50% or half binding, extrapolate over, hit the curve, come down, and you can get the binding constant. All right, so one other important thing before we kind of wrap this up is, how does the binding constant relate to the free energy of binding? Or how are we going to do a thermodynamic analysis to determine what will make a protein ligand complex tighter or looser, high affinity or low affinity? So really this ties back to what we've done before. We can do a thermodynamic analysis. And in this case, think about free energy of binding, delta G, is R times T times natural log of the binding constant, K sub D. Very important equation. Very important equation. So let's just kind of cut to the chase here. The more negative the delta G, the more negative delta G. Now, how do we get a negative delta G? This goes back to what we've done over and over and over again. A more negative delta H will lead to a more negative delta G, and a more positive delta S will lead to a more negative delta G. So all these things, the more negative the delta G is, the more spontaneously the ligand will bind to the protein. That will lead to a lower K sub D. So lower K sub D equals tighter. We just said this, but let me re-emphasize this. Tighter the protein ligand complex. And really we're saying there's more affinity. A higher affinity between ligand and protein. In general, and this is done at 25 degrees Celsius, a 1.4 kilocalorie per mole difference in delta G can lead to a 10-fold difference in binding constant. So that's just kind of a rule of thumb that has been determined experimentally. So we're going to talk a lot about ligands binding proteins, enzymes binding substrates, ligands binding protein receptors that you've done in other classes. Binding constant is a very important, I guess, description of the affinity for the ligand for the protein. And we can go all the way back to thermodynamics that we've talked about. The more negative the delta G associated with the ligand binding the protein, the lower the binding constant and the tighter the protein ligand complex. And again, we can trace the more negative delta G back to an enthalpic and entropic components that we've done before. All right, so this finishes up the Chapter 5 start notes. We still have the MHC Class 1 proteins that we will do in class. That will also be part of Chapter 5, but they will be a separate set of notes because I've put them all together separately. All right, thank you.